Okay, I would like to briefly introduce our second module for this class. It's a model of spotted owl population. Now, before we had an interacting system of owls and rats. Now we're just looking at spotted owls in 3 stages of life. Here are various references that talk about biological background of spotted owls if you're interested. This reference is important. We'll be using this later. This actually has a more realistic model of owl populations, and I will be asking you to implement that on a spreadsheet. All right, here's again some summary biological information. What we're important here is that we are modeling the number of female owls. Of course, the number of males and number of females should be approximately equal, so it should be good enough to model the number of females. And we're modeling the females at 3 stages of life: juvenile, that's birth to juvenile; subadult, that's single owls but are of breeding age; and adults. Okay, and our time interval is yearly. So if you remember in our previous model we had a time index k. In this case, k will represent years. Okay, so here's the classification of the different categories. And this describes how the populations interact. It's really quite intuitive. A certain population of juveniles survive to become subadults. This actually should say subadults instead of adults. Okay. Then a certain proportion of subadults become adults, and then a certain proportion of adults will give birth to juveniles, and that proportion of adults will also survive. Right? Now, we have here a system diagram that I'll show you, and this system diagram really summarizes what I just said. This circle here represents juveniles. This circle here represents subadults. This circle here represents adults. Okay, and J, K, S, K, A, K represent the respective populations at time K. Now, suppose you have one individual in this juvenile population at time K. What this arrow means is that there's a probability P that juvenile will become a subadult. Now, P is certainly going to be less than 1, because you can't have more owls surviving to subadulthood than there are juveniles, and some of the juveniles, of course, will die. So P is actually a positive number, so I could say 0. P is between 0 and 1. Okay, similarly, a certain probability, or I should say, for each subadult, a certain probability will survive and become an adult at the next time. So here again we have Q, where Q is between 0 and 1. Right. Now here we have adults. Adults, we have 2 arrows to explain. Here's this arrow that goes from the adult category back to itself. What that means is that with probability U, an adult in this category will survive until the next year. So here again we have U is between 0 and 1. It's positive. On the other hand, an adult female has a probability R of giving birth to another owl. So that's where this R comes from. Each adult owl in this category, there's a probability R that at the next time that owl will engender an additional juvenile. And we're also supposing that R is between 0 and 1. Actually, owls sometimes lay more than 1 egg, but we are going to assume that the birth rate, yearly birth rate, is less than 1. Okay, so this diagram is a very good way of summarizing the information in this system, and we'll be using these system diagrams quite a bit. They're very often used in engineering. And here's the interpretation of PQRU according to the explanation that I gave. You can read that explanation at your leisure. Also, here's the explanation of the populations. As I mentioned, JK, SK, AK are juveniles, subadults, and adults. Okay, so this is called a life stages diagram or transition diagram. It's used in populations. It's used in industrial engineering to do manufacturing flows. It's useful in many, many contexts. So this is a very useful tool. Okay. Now in this case, we have a mathematical specification which is very similar to the specification of the owl-rat model. XK represents the populations of juveniles, subadults, and adults at time K. Now, the populations of juveniles, subadults, and adults at time K plus 1 is related to the populations at time K by a matrix. And this matrix is formed using these coefficients P, Q, R, and U. Right? Now, we can write algebraic equations according to this diagram. For instance, what does this P represent? This P represents that the number of subadults at time K plus 1 should be equal to P times the number of juveniles at time K. Right. This Q represents that the number of, I'm sorry, I haven't shown everything. Let me start again here. Let's focus on this subadults here. Okay. All right, this arrow with a P that goes into this category, subadults, indicates that the number of subadults at time K plus 1 should be equal to the number of juveniles at time K times P. Okay. Now, this adult category, there are two arrows into this adults category. What does that mean? The adults at time K plus 1, some of them are due to subadults at the previous time, and some of them are due to adults that survive from the previous time. So this arrow and this arrow indicate that AK plus 1 should be equal to Q times SK plus U times AK, because a proportion Q of subadults survive to adulthood and a proportion U of adults survive until the next year. Okay. Finally, we have this arrow into JK. What does that represent? That means that the juveniles at time K plus 1 are all due to adults at the previous time. So juveniles at time K plus 1 should be equal to R times adults at time K. Now I said that in words. Here's the same thing in writing. Okay. And we can write this as a matrix, of course. I don't know why the things got lost, but we can write this as a matrix like this. This is the vector xk plus 1. It has three components for j, s, and a. This is the vector at time x at k, j, s, and a. And here's the transition matrix. Okay. All right, now, once we have it in this mathematical form, it's pretty much the same deal as we had with owls and rats. We have this matrix vector form of the equation. And we can use the eigenvalues and eigenvectors to give us the behavior. Okay. In this case, you can use Wolfram alpha or some other method to find the three eigenvalues. It turns out that one is real and two are complex. Now, we saw complex eigenvalues before, and we know that that gives kind of behavior that makes the system rotate around. Actually, I think it rotates the other way, but it makes the system rotate around. Okay. Now all of these eigenvalues have absolute value less than 1. Now, we saw that eigenvalues that have magnitude less than 1 correspond to shrinking populations. Okay. So, in fact, in this system, the population of owls will inevitably shrink. All right. Notice that the survival rate of juveniles is very low. Now, if we increase the survival rate of juveniles, we get a new matrix here. Okay. And we can compute the eigenvalues. Here's our largest eigenvalue at 1.1. Okay. And we saw that the largest eigenvalue drives the eventual behavior of the system. So eventually the spotted owl population will grow at about 10% per year. Okay, so that's a summary, and next video I'll show you some activities that we'll be doing.